do the comparison of hydrolysis. So Skinner, what we did was so far, okay, there were 3 chlorine related compounds whose hydrolysis we had to whose hydrolysis we had to whose hydrolysis and the mechanisms we had to compare. The first one was that chlorine with benzene had no hydrolysis. Halogenoalkanes, this hydrolysis you've already studied in a lot of detail, SN1, SN2 mechanisms, and we're going to go over them again. And the last one was acyl chlorides, which you have never studied actually, and they had vigorous hydrolysis. So the first one we talked about was Chloro Benzene, and I told you that it absolutely has no hydrolysis. The benzene electron cloud and chlorine's lone pairs, they kind of mix up. It's got lots of lone pairs. There's a lot of electron cloud over here. There's a lot of negative charge. So the OH-1 are nucleophiles are not even going to come close to it. They're going to be repelled. So that's your nucleophile. It's not going to be attracted to either water or OH ions. The lone pairs are going to be as far away from these electrons as possible. So the Cl overlap and the bond becomes stronger and has greater negative charge density. So the nucleophiles are going to be repelled. And then we started talking about halogenoalkane. And I started talking about nucleophilic substitution, which were SN reactions. That if you have a halogenoalkane and you add OH in the form of NaOH aqueous and reflux, the Cl would be substituted by, so this Cl is going to be substituted by NaOH. That's what's going to happen. So it's going to be substituted by NaOH. And that's the reaction. We discussed that your halogens, their hydrolysis becomes more vigorous if you've got iodine down the group. It becomes more vigorous. Why? Because iodine has a weaker bond. It's a bigger atom. It's got a weaker bond. Cl has a much stronger bond, so its hydrolysis is kind of more difficult. So, anyways, you've got a primary halogenoalkane which has SN2 mechanism. We're going to discuss that first. So let's start talking about SN2 mechanisms in detail again. And this is something which you have already done in AS and which is going to come in your A2 exam as well. So primary halogenoalkane. Here, let me put so primary halogenoalkane. And the thing with this is, I think I should start on the next page. So the thing with this is that if you look at a primary halogenoalkane, it's got just one carbon chain. So it's CH3. It's got a carbon which is bonded to a Cl, and this carbon is bonded to 2 H atoms. And this bond is highly polar. Carbon is positive and Cl is partial or very slightly negative. Now, the thing that's going to happen is that if you add an OH-1 nucleophile, the lone pairs of this OH-1 are going to be attracted to this carbon atom. And the electrons over here, they are going to be further repelled as this OH-1 approaches. So that's the first step of the reaction, that the OH comes close to the Cl, comes close to the carbon atom, which is highly polar, and it tries to bond with it. And because of the negative charge over here, the electrons over here are going to get repelled. So that's the first step. Next step is that there's going to be a transition state that's going to be formed. So let's keep this here. And it's going to form a transition state. What is that transition state? What's going to happen in that transition state is that the OH will slowly bond with it and the Cl would slowly break off. Slowly it's going to break off. So you show it with a dotted bond. The OH is trying to bond with the carbon atom and the Cl is trying to leave. And it's going to have, this entire thing is going to have a -1 charge. And that's known as your transition state. TK, is this clear? Do you remember this stuff?
Yes, sir.
And in the next part, the Cl will eventually, it will leave. It's going to break off. 1 second. So it's going to eventually leave. It's going to take its electrons and it's going to go away. So what's going to be formed is that the OH is going to eventually take its place. So this part, the Cl has left and the OH is going to come in and bond with that particular carbon atom. That's it. So that's what's going on. So that's one. And you've got this one over here. So your entire mechanism is now complete. Remember, it's a one-step reaction. It's all the reaction happens in exactly one step. So it's a one-step reaction. The transition state doesn't mean it's not an intermediate. It means that somewhere in the middle, this might be happening. It doesn't really actually exist. I mean, it's just a transition that's happening. The OH comes in and the Cl gets knocked out. So, I mean, this just shows the OH coming in and the Cl getting knocked out. That's it. So in the reaction, you don't actually see this thing getting formed. It's either this or this. Okay. So is the mechanism clear?
Yeah.
Okay, that's the mechanism for primary halogenoalkanes. Now, about this mechanism, there are two things. One is, why does this happen? That's the question. Why is there not a carbocation? So why is a carbocation not formed? Now, the answer to that particular question is that, I mean, basically the question is, why doesn't this happen? Like you've got CH3 and you've got H and you've got a Cl. And the question simply is, why doesn't the Cl just break off on its own first? And then in the next step, a carbocation is formed. And the Cl has broken off. And why doesn't the OH -1 come in? And bond with this. See, that's the entire question. Why doesn't this happen? And the reason for that is this carbocation is kind of it's very unstable. You've got a very unstable carbocation, and the explanation for this specific question is, the specific answer to this question is, second. So the specific answer to this question is that the carbocation has fewer alkyl chains. Fewer electron donating alkyl chains. Hence, it has high charge density. Making it unstable. This is the answer that you're going to write in your exam. Now I'm going to explain the reasoning behind this. The reasoning behind this is, why is it so hard for the Cl to leave on its own? Remember, the carbon over here has a very strong positive charge. I mean, it's got a very strong positive charge. The positive charge is so strong, and there's a reason why it's got a strong positive charge. Even over here, this is a polar bond. So I'm just going to explain the reasoning now. Even over here, it's got a very positive, it's a very polar bond. So the positive charge on this carbon is very strong because it's not surrounded by large groups. Those cytopena, they are H atoms. On two sides, they're H atoms. H atoms don't have electrons. So around it, there's not a lot of electrons around it. There's only one carbon chain. So around it, there are no large groups. So there's no one giving it electrons, which is why if it's not surrounded by electrons, the positive charge is really strong. Is this point clear? This point, the first point?
Yes, sir.
Yeah.
Okay. So the positive charge is really strong because no large groups around it. So if the positive charge is really strong, that means the negative Cl over here is going to be attracted very, very strongly to it. So it's probably not going to be possible for it to just leave. The attraction between the two is going to be really strong. So it's going to be very difficult for the Cl-1 to actually just leave on its own because of the very strong positive charge over here. So which is why you would need OH-1 to come in. OH-1, the negative charge of the OH-1 is going to, not only would it be very strongly attracted to the positive carbon atom, but it's going to provide the push that's going to be needed to push the Cl out. Is this point clear?
Yes, sir.
Okay, so just remember, because this carbon is not surrounded by large groups, the positive charge is kind of really strong. And because the positive charge is really strong, it will attract the Cl really strongly. It's not going to let it go easily. And because it's got a positive charge that's very strong, it will immediately attract the OH-1 as well. And the OH-1 will provide the necessary repulsion to knock out the Cl. So the OH would come in and then the Cl will get knocked out. Because of the stronger positive charge over here, it would be very hard for the Cl to leave on its own. Okay, so is that point clear, everyone? Bakiyon clear?
Yes,
Lubanis is clear? Ethan, Mohammed is.
Yep.
So the carbocation is probably not going to form because it's got a large positive charge. And the Cl would immediately get attracted back again. So kind of very hard for the Cl to actually leave. So which is why a carbocation is not formed. because it's got fewer electron donating alkyl groups, chains. It's got high electron charge. It's got high positive charge density. Let me add the positive word. So it's got high positive charge density, making it very unstable. So the next one that we're going to talk about is the tertiary carbocation or the tertiary halogenoalkane. That one is going to have a different mechanism. So let's talk about a tertiary halogenoalkane now. Now this one was your SN1 mechanism. And what goes on in tertiary halogenoalkanes. So now the issue is, in the tertiary halogenoalkanes, you got a carbon atom that's surrounded by carbon chains on all sides. So it's a carbon chain on top, a carbon chain on the left side, and it's got a carbon chain at the bottom as well. And you've got a Cl. Now over here, it's a lot more feasible that the Cl is going to be leaving on its own. Reason being that the positive charge on this carbon atom is not really strong. Why is it not really strong? Because when this carbon atom got a positive charge, it had carbon chains on all sides. So it's got electrons over here, electrons over here, electrons over here. So it's got an electron cloud on all sides. So the electron cloud is going to be pulled in by the positive charge, and the positive charge density would decrease. So if Cl decides to take away electrons, this carbon has other places where it can find those electrons. It's not in need. It's not desperately clinging on to these electrons. So if this Cl decides to take away the electrons, this carbon can easily get electrons from the other carbon chains. The electron cloud could be pulled in, and it wouldn't really feel the loss of electrons. Is that point clear?
Yes.
Okay.
Yes.
So you'll have something like this. You'll have a CH3. And the Cl-1 breaks off. And because the positive charge is really strong, it's not going to attract the nucleophile immediately. Like the OH-1 nucleophile will find a little attraction for that positive carbon in the middle because it's got a small positive charge. So the carbocation would be kind of very stable. And now the OH-1 would come in. Now it's got a full positive charge. OH has these lone pairs, and they're going to get pulled in now. And that's when the reaction would be complete. So the OH has nothing to do. It's a two-step reaction mechanism. And you can draw the last. So the OH will eventually join in. And this is an actual carbocation intermediate that is formed during the reaction. That is formed during the reaction. So is this clear? This one?
Yes, sir.
I said, just hold on, give me 20 seconds. So that's an actual carbocation intermediate, and just wanted to add that it's a stable carbocation intermediate. So you can write everything that was wrong with that one. Everything is right over here. Stable carbocation. It's got more alkyl chains, more electron donating alkyl chains. This has got more electron donating alkyl chains, which is why what's going to happen is that it's going to have a lower charge density. That's it. That makes it stable. So when Cl leaves, it can arrange electrons from elsewhere. So the positive charge is not going to be that much of an issue. The positive charge would be smaller. It's going to have a lower positive charge density. Positive, you can add the word positive here. So lower positive charge density. So hopefully, is this all clear?
Yes, sir.
I said secondary halogenoalkanes kind of have a mixed mechanism. It depends on a lot of things. So the second, I'll just make a point here that that secondary halogenoalkanes have both SN1 and SN2 mechanisms. Both of them. And now one other important point about this is that this hydrolysis is happening. But one very other important point about this is the shape or the chirality of the molecules. Okay, there's one point about chirality, and that is, let's make that point, and that is that let's discuss chirality over here. So chirality and mechanisms. The mechanisms that we are talking about. Now, let's say we have a chiral. Let's talk about a secondary halogenoalkane. Let's talk about a secondary halogenoalkane, or just any halogenoalkane. I'm just going to discuss, depending on the mechanism, what type of chiral molecule would be formed. So here's a carbon chain. And there is a CH3 over here. And there's a Cl. And there's an H. Now this clearly is a chiral carbon atom, right? But the thing is that if you use the SN2 mechanism, it leads to one chirality, or leads to one type of chiral carbon atom. It leads to one type of chiral carbon atom. And I'm going to explain that. Let's say you have this molecule, right? The three-dimensional shape of this molecule is this thing. It's an H with a Cl, and it's got so it's got a CH3, and it's got this carbon chain, which is CH2 and CH3. So right now it's clearly a chiral carbon molecule. And what's going to happen here is, let's assume the OH comes in. The Cl is partial negative and the carbon is partial positive. And let's say it's an SN2 mechanism. The OH comes in and the OH minus one comes in and starts to attack this carbon, which is positive. And the Cl takes away its electrons, right? Now, what will happen is, now listen to this carefully, the OH is always going to attack from the opposite side. It's always so it's always attacking from the opposite side, because this side is the negative side. So the OH minus one is going to come from the other side. So the Cl breaks off. So what's happening is that if I redraw the molecule, the Cl gets knocked out. Okay, so let's quickly figure out what's going to happen over here. And listen to this very carefully, that so let's assume that the Cl gets knocked out. Okay, I'm just drawing the whole thing in one step. So the Cl is gone. And the OH is now trying to bond. So the OH is going to come in and it's going to try and bond with this carbon atom. What will happen to the other bonds? All the other bonds are going to get repelled and they'll be pushed to the other side, because the OH is coming from the left, right? So what would happen is that this CH3 is going to get repelled and it's going to go to the other side. It's going to be pushed to the other side, right? Same goes for CH3, CH2. According to valence shell electron pair repulsion theory, the CH3, CH2 would also get repelled and it will be pushed to the other side. The same happens to H. The H atom also gets pushed to the other side. So the point is that the OH minus one nucleophile, and let me just make this shorter. Okay, can I? So the point is that the OH minus one nucleophile, which is coming from the opposite side, is going to come from this side, attack it from the exact opposite side. The Cl gets knocked out, so the Cl just runs away, taking the electrons away with it. The OH minus one tries to bond with the carbon atom, and all the bonds, they get pushed to the other side. Is this clear?
Yes, sir.
Yeah.
So the thing is, you always get one type of chiral carbon atom. That's it. I mean, this one. Because the OH minus one would always be coming from this side. So the entire bonds, all the bonds are going to be pushed to the other side. It's still going to be a tetrahedral structure, except for the fact that just 1 second, let's shorten this. So except for the fact but the thing is, it's always going to be one type of tetrahedral structure. That's it. All the bonds get pushed to one side, and always one type of tetrahedral structure is formed. So not the mirror image. So always one type of chiral. And that's your SN2 mechanism. It always leads to just one type of chirality. Because the atom over here, it's like your, it's going to be direction dependent. Like if Cl is pointing here, the OH would always come from the opposite side. So you're not going to get two different types of molecule or two mirror images. You're always going to get a single type of, it's going to be chiral, but it's just going to be one type of chiral, not the other type, not the mirrored version. Is that clear? This thing?
Yes, sir.
And the mirrored version I'm talking about is the other one. It's this one. The mirrored version of this left to right inversion would be this one. That you have a carbon atom and the CH3 is pointing this way. And so the CH3 is pointing this way. The CH2, CH3 is also pointing this way. The H is also pointing this way. And the OH is coming from the other side. Okay, that's the mirrored version of the above molecule. So you're not going to get this. Why? Because the OH is not going to attack from this side. It's not going to come from this side. It's not going to push the other groups to the left. It's going to attack from the opposite side. So hopefully this should be clear. SN2 mechanism. TK, just remember that. Any questions about this? Or Lubena, is this clear?
Yeah.
But the other one, SN1, we'll discuss that in the next class then, TK. It's going to take a long time. So just remember about chirality, that SN2 mechanisms, it always leads to one type of chirality. Sakib, it's better to use notes. Plus, a lot better to use notes. ठीक है, इसमें I'll share board links, ठीक है, जो यहाँ पे ना दिए हुए हैं, इक्विलिब्रिया के इलेक्ट्रोकेमिस्ट्री बोर्ड लिंक, I think इक्विलिब्रिया का पूरा है. We haven't done transition metals, but organic we have got lots of notes, ठीक है, so study from those. And you can convert these into PDFs as well. वो मैं से पूछ लेना topic wise, I'll send them, ठीक है. चलिए, let's continue tomorrow. Okay, then take care.
Thank you.
Hafiz.
Hafiz.
Hafiz.